Hello everyone, my name is Dr. Manisha. I'm an assistant professor in Department of Chemistry, Maharaja Agrawal University. Today, I'm going to discuss about the basic concepts and instrumentation of spectrophotometry. Whenever there is interaction of light with a chemical substance, there are certain phenomena that are observed, such as absorbance, reflectance, transmittance, diffraction, diffraction. The branch of electromagnetic spectroscopy, which measures how much light a chemical substance absorbs by measuring the intensity of the light as the beam of light passes through it, is known as spectrophotometry. And the instrument that quantitatively measures the amount of light absorbed or the intensity of the color at a given wavelength is known as spectrophotometer. Spectrophotometer consists of two parts, spectrometer and photometer. Spectrometer is to produce light of any wavelength, while the photometer is to measure the intensity of the light at different wavelengths. These quantitative measurements are made in terms of transmittance and the absorbance. First of all, coming to electromagnetic radiations, these radiations consists of the electromagnetic waves which are synchronized oscillations of electric and magnetic fields. As you can see in the diagram, whenever there is periodic transition of electric and magnetic field, electromagnetic radiations are observed. The relation between the energy and wavelength is given by E is equal to hc by lambda. So, longer the wavelength, lower will be the energy, and shorter the wavelength, higher will be the energy. This is the electromagnetic spectrum. Different type of radiations, when are arranged in terms of increasing wavelength or decreasing frequencies, we call it an electromagnetic spectrum. Whenever these radiations interact with the substance, certain type of interactions or transitions are observed. For example, if we talk about gamma rays, X-rays, UV rays, visible rays or near infrared rays, electronic transitions are observed. While the infrared radiations results in the molecular vibrations and microwave radiations results in the molecular rotations, and radio waves results in the flipping of the nuclear spin. So, depending on the radiation which we are using, different type of transitions will be observed. This is a generally observed electronic transition in the spectrophotometry. These are all electronic energy levels. Sigma and pi represent the bonding energy levels. N represent the non-bonding energy level. Pi star and sigma star represent the anti-bonding energy levels. So, depending on the radiation which we are using, different type of transitions can take place. For example, if you are using higher energy radiations, sigma to sigma star transitions can be observed, while for the lower energy radiations, N to pi star or N to N star transitions can be observed. Most of the absorption spectroscopy is based on the N to pi star or pi to pi star transition. So due to this reason, most of the transitions fall in the typical UV visible absorption range, that is 200 to 700 nanometers. This is the plot of absorption data. The plot is plotted between absorbance and wavelength. The maxima of the peak represent the wavelength at which the transition take place or the energy was absorbed. As I have already discussed, the quantitative measurements are done in terms of absorbance and transmittance. Discussing about these, transmittance measures how much of the light is transmitted. The higher the amount of the light that passes through, the larger will be the transmittance. Transmittance is defined as the ratio of the intensity of the incident light to the intensity of the transmitted light. And absorbance measures how much of an incident light is absorbed when it travels in a material. Absorbance is defined as the logarithm of the ratio of the incident to transmitted radiant power through a sample, excluding the effect on the cell walls. If we talk about the mathematical expressions, transmittance is given by the equation T is equal to I by I naught. As you can see in the diagram, I naught is the initial light intensity, I is the intensity of the light after it has gone through the sample, and the path length, which we have designated as B, is the length which the light travels while absorbing sample of the concentration C. Absorbance is related to the percentage transmittance as A is equal to minus log T. These are the equations. T is equal to I by I naught, and that is also equivalent to 10 raised to power minus of absorbance. Percentage transmittance is equal to I by I naught into 100, and A is equal to minus log of T. A sample calculation is shown here. If percentage transmittance is 95%, then absorbance will be 0.02227. So you can see higher the transmittance, lower will the absorbance, and vice versa. A very important linear relationship was given by Beer and Lambert between absorbance and concentration of an absorbing species. This is known as Beer-Lambert law, and it is represented as A is equal to ABC, where capital A is the absorbance, small a is the molar absorptivity, also called as extinction coefficient, and it depends on the material being studied. B is the path length. The diameter of the cuvette or the sample holder is the distance the light travels through the absorbing substance. So if the same size cuvettes are used, the path length will be constant. C is the concentration of the sample which we are studying. Now coming to the instrumentation, this is the typical instrumentation of the spectrophotometer. The lamp emits all colors of light, and these are then passed through the monochromator, which selects one wavelength, and that wavelength is sent through the sample. The detector then detects the wavelength of the light passed through the sample, and the amplifier then finally increases the signal so that it is easier to read against the background noise. Now coming to the types of the spectrophotometer, these are basically of two types: single beam spectrophotometers and double beam spectrophotometers. In single beam spectrophotometers, all the light waves coming from the light source passes through the sample. So if we want to measure the intensity of the light, the sample must be removed so that the reference can be placed each time. It is a bit time consuming, but these are less expensive and simpler to use. Another one is double beam spectrophotometer. Here, the light beam splits into two parts, and only one part passes through the sample and the other part passes through the reference. It is more advantageous as both the sample and reference readings can take place at the same time. Now, depending on the wavelength of the light which we are using in the spectrophotometer, these are further divided into few categories. One is visible spectrophotometer. Here, the wavelength range which is used is 400 to 1000 nanometer, that is visible light vision range. The visible spectrophotometer is a single beam spectrophotometer. It is used in multiple fields like medicine and health, food production, environmental monitoring, and so on. Another one is UV visible spectrophotometer. Here, the measured wavelength range is 200 to 1100 nanometer. Based on the principle of UV visible spectrophotometer, here the radiations in the UV visible region are absorbed by the substance which we are studying, and the optical path of the product can be divided into single beam, pseudo double beam, and double beam. Another one is IR spectrophotometer. Here, the general infrared spectrum refers to the infrared spectrum greater than 760 nanometer. This is the most commonly used spectral region for studying organic compounds. So it can be used to analyze sample in various states such as gas, liquid, and solid. The spectrum has the characteristics of fast speed, small sample amount, and strong characteristic, and also it causes no damage to the sample. Fluorescence spectrophotometers are used to scan the fluorescence spectrum emitted by the liquid-like fluorescent markers. They provide many physical parameters such as emission spectrum, fluorescence spectrum, quantum yields, fluorescence lifetime, so they can reflect the bonding and structure of the molecules from various angles. Last one is atomic absorption spectrophotometer. This instrument analyzes the metal elements based on the effect of the atomic vapor of the ground state of the substance on the characteristic radiation absorption. Here, the light source emits the characteristic spectral radiation to be measured, which is absorbed by the ground state atoms of the measured element in the sample vapor after passing through the atomizer. The content of the measured element can be obtained by measuring the size of the characteristic radiation absorbed. They are very reliable and sensitive in nature, so they can be used in detection of trace elements. These are the few applications of the spectrophotometer. They are used in the detection of the concentration of the substances. They are used in the detection of the impurities. They are very helpful in the structural elucidation of organic compounds, monitoring of dissolved oxygen content in fresh water and marine ecosystems can also be analyzed using spectrophotometer. They are used in the characterization of the proteins and detection of the functional group. So they have wide range of applications which can be utilized in various fields. Thank you so much.